Okay, hello there. So, this is another episode in the series of modern physics, which I've called What is the Problem with the Famous Equation E equals mc squared? This video could be seen a little bit as a follow up to my previous video, which I made on special relativity, where I ended on a somewhat vague note regarding this formula. It's this relationship with special relativity and its origin in classical electrodynamics and its validity in itself. And this time I've done a little bit of homework, so hopefully now I will be able to give my own opinion about this equation much better. And my conclusion after having studied this a little bit is that I don't think this formula represents good physics. And I think also there's a rather simple argument you can put forward to show that, and that's what I'm going to do in this video. Um, let's just hide that for a moment. So just to talk a little bit about its relation to special relativity, you can arrive at it starting from the Lorentz transformation, where you pretty swiftly arrive at a formula for the relativistic momentum. And then you can do further formula manipulations to arrive at an energy formula, which you then Taylor expand to obtain this series. And here we have a familiar term, which is the classical kinetic energy, and then this constant term here, which we recognize and which has been, interpreted as the so-called rest energy of the particle. But I'm not going to talk any more about this. If you want to see this in more detail, there are presentations on YouTube and elsewhere. A little bit about, the history of the equation. This could be an entire episode of its own. So I'm just going to mention a couple of names. We have Oliver Heaviside, Henri Poincaré, and this relatively obscure Italian Olinto de Pretto, which was often, or which was sometimes mentioned as the precursor to this formula. That he was in fact, well, several people were before Einstein in presenting this equation. But since, well, my own conclusion, my own opinion about this formula is that it's not really good physics. So this question about the who came first isn't that interesting to me, isn't that engaging. So I will not talk very much about that also. The only thing in these early derivations that I think could be worth pointing out here is that in the year 1900, Poincaré derives the law of conservation of momentum within classical electrodynamics. And the point there being that in if you dig deeper below just interaction between massive particles, you arrive at a more general form of law of conservation of momentum, where it's not the total momentum of the massive particles that is conserved, but it's the sum of the momentum of the massive particles and the momentum carried by the electromagnetic field that is conserved. And he points out that if light is assumed to have a mass of this magnitude, then you could apply the usual formula for momentum, which is this, to calculate the momentum carried by the light. Um, so that is arguably one of the first times when the formula appears. But of course, we should emphasize that he is not saying here that massive particles have a rest energy, but rather he's saying that if we interpret the energy of the electromagnetic field divided by c squared, then that could be representing somehow the mass of the light, and that's another statement, of course. But this, you may speculate that this could have been an inspiration for later, assuming that mass carries energy. So we'll do a case study here with alpha decay, and I will follow a standard textbook approach to this, where you use this very formula, this E equals m squared. We have a parent particle, which then decays into a daughter particle and the alpha particle. And the energy released is calculated as the difference between the mass of the original particle minus the masses of each of those decaying particles, and then you multiply it with c squared. And we speak then of a mass deficit. It's actually assumed now that the total mass of the two particles after decay is less than the total mass of the, and here we see the same formula again. So if we just work out the kinematics here in the rest frame of the decaying particle, and we are, I mean, of course, at liberty to assume that these particles will sort of after the decay move in the y direction, and the energy released will then be sort of kinetic energies of these particles in the y direction. And since it's a two-body problem, these values, these velocities will be uniquely determined just by knowing this amount of energy that is released. And of course, before decay, we have energy is just the rest mass in this, paradigm system. And then the rest mass is after decay, represented by this. Yes, here we see these formulas again. But now, if we change perspective and view the situation in a reference frame that is moving in the x direction. So if we then write down the total energy, well, in before decay, we will have the same rest mass term here, plus, but here's the difference, we have also a kinetic energy term in the x direction. After the decay, well, these terms are what they are. They will not be affected by the fact that our reference frame is moving in the x direction. So these terms cannot change, but there will be a kinetic energy term in the x direction here too. But maybe you see the problem now. Well, since we assumed that the mass of the parent particle was larger than the sum of these, this term will be larger than this one. And that means that we, in this system of reference, will lose energy which we cannot account for. Where did it go? And that, violates the law of conservation of energy. Now, am I the first to point this out? When I was browsing through these articles, I actually came across the following quote from allegedly from Max von Laue. One type of energy the new physics must eliminate from its list is kinetic energy. The reason is that if mass is based on energy, as E equals mc squared shows, then there cannot be a kinetic energy, k equals 1/2 times the mass times the velocity squared, which in turn depends on the mass. And I think that is precisely what I showed here. So, of course, somebody might point out, well, you're using classical kinetic energy. Well, as far as I can judge, the argument wouldn't change even if I used some relativistic formulas here. So that's the conclusion actually here, that regardless of who derived this and by which manner, it's simply not good physics in my opinion, and apparently I'm not alone in thinking this. We can talk a little bit about, I mean, what is the nature of the mass deficit that people play around with here? And there could be a misconception that there are elementary particles vanishing. I mean, if we view a neutron as essentially a sum of a proton and an electron, then the sum of the elementary particles, electrons and protons, are the same before and after the decay. So the mass deficit just comes from an assumption that the parent particle has a greater inertial mass just because it has a greater internal energy. And given this observation, we can start to speculate. I mean, have we been in a circle where you prove things by definition? I mean, how many of these nuclear particles, I mean, have we actually measured directly the inertial mass? Or have they been derived indirectly, assuming the validity of this formula? Now, there are people who have investigated this. I can show you this. You can easily search for it on the internet if you're interested in digging deeper into this. But here it is claimed we only have a deduced estimate of the neutron mass based on the mass energy equivalence. To date, we have not measured the true mass of the neutron. His claim, I don't know. Another example where it seems that this relativity physics has led modern physics in a strange direction was, when they essentially invented the neutrino particle to account for missing relativistic kinetic energy. And if you want to dig deeper into that issue, well, here is a paper by the same author, which I recommend you reading. So, yeah, that was my conclusion. Now I've covered at much greater depth, I think, the issue of E equals m squared. And I hope you enjoyed it. So that will be it for me now. And I say bye bye.